Okay. Hello, everybody. So Dr. Naimul Khan is an associate professor of electrical, computer, and biomedical engineering at Toronto Metropolitan University, which is formerly the Ryerson University. He directs the Multimedia Research Lab. He's also a cross-appointed at the Creative School through the Masters of Digital Media program. He obtained his PhD in electrical and computer engineering from Ryerson. It doesn't say here. He obtained his MSc from University of Windsor. And I'm happy to say that he is my former student as well. And I'm happy that he's progressing over there. He obtained his BSc from Boit in Bangladesh and Bangladesh University of Engineering and Technology. His research focuses on a user-centric intelligent system combining AI, computer vision, and augmented or virtual reality. He has an impressive record of publication in premier multimedia, AI, and health informatic venues, and a rich history of industry collaboration. With media and healthcare companies in Toronto and beyond. He is able to obtain about 3.5 million in government funding from NSERC, OCE, MITEX, and CSIRC. Notable projects he has been able to do is they include physiological signal analysis for arrhythmia detection with the Mount Sinai Hospital and DAPAsoft Incorporated. Non-pharmacological anxiety reduction with biofeedback based on AR, VR games, and many others. So I'm not going to go through the list because it's bio is a long bio. His research work has been featured in the media multiple times due to the broad practical impacts of the project. For example, in the University of the Toronto Star, the Toronto Sun, Globe and Mail, and TMU News. He is a recipient of the Best Paper Award at the IEEE International Symposium on Multimedia 2017, the Best Paper runner-up at the IEEE CVPR workshop in 2021. These are all premier conferences. TMU's Dean Research Award of 2021, OCE Talent Edge Postdoctoral Fellowship, and several other awards. He's a senior member of IEEE and a member of the IEEE Signal Processing Society and IEEE Engineering and in Medicine and Biology. I'm happy to introduce that Dr. Khan is going to give a talk towards virtual reality-based therapy and training using machine intelligence. Here you are.
Thank you, Dr. Ahmed, for the amazing introduction. I'm sorry for the long bio. I didn't realize that it will be read out. I would have shortened it, but it's great to be back and doing a talk at Windsor Computer Science. As Dr. Ahmed mentioned, I was his student. I did my master's from Windsor, and the room you are sitting in, I was in that same room about like 14 years ago. So that makes me very old, but so yeah. So I'll share my screen and start my presentation. Just give me 1 second. Can everyone see my screen?
Yeah, we're good.
Okay, perfect. So welcome everyone to my talk. My topic is virtual reality-based therapy and training using machine intelligence. I'm a director of the Multimedia Research Laboratory and associate professor at TMU, as Dr. Ahmed has mentioned. So, so the overarching theme of the talk will be digital therapy, right? So why do we need digital therapy, right? So essentially, my lab has been focusing on using digital therapy to reduce stress, right? So stress affects everyone, and In particular, we work with a lot of vulnerable and high-risk professions, for example, nurses, doctors, police officers, and also vulnerable population, right? For example, I have two projects on, one with kids with special needs, one with refugee youth, right? And with the unexpected events like COVID-19 has actually resulted in a big spike in mental health related issues, which creates a huge burden on the healthcare system. So that's essentially our focus, that how do we reduce this burden? So if you look at this chart that was published by like OMA, Ontario Medical Association in 2021, as you can see that the pandemic has created a severe backlog in healthcare services. So like, as you can see, it's pretty obvious from the numbers, and mental health is a big aspect there as well, right? Digital therapy, what digital therapy can help is that it can create pathways to treatment approaches that are scalable and accessible. So both these two words are very important, that by scalability, we mean that treatment plans or policies that can be scaled up very fast because we have the number. The number is a big issue here, right? And it has to be accessible as well. So we don't want to, like, for example, we have a lot of remote areas in Canada, even internationally, we have some international projects as well, where they may not have access to healthcare professionals right away, right? Like especially mental health related issues, right? With mental health related issues, right? So it's time saving for both client and healthcare professional, and also in future, like not now, right now, but digital therapy tools with AI backing can enable self-management. So for example, if the tools have enough AI baked into them, right, the patient can probably do some sessions of the treatments themselves. That's where the self-management aspect comes in handy, right? So what is the role of virtual reality in digital therapy, right? So virtual reality essentially increases the sense of immersion that we have, right? So the sense of immersion, again, like virtual reality has been around for a long time, right? Like it's been mainly being used in game, right? So which, again, sense of immersion is important. But for therapy, for example, one project we work on is cognitive behavioral therapy. So for any type of therapy type of scenarios, immersion becomes even more important, right? For example, if you are afraid of a spider and I want to slowly, gently introduce you to spiders crawling around in a room, it's probably going to be a lot more scary in VR compared to on like a traditional screen, right? So this is why VR has been proven to be more effective in that type of scenarios, right? That's number one. And number two is that VR headsets provide us some additional modalities of data that can be useful for stress assessment and evaluation. For example, we have eye tracking data, where you are looking, how fast you are blinking, how big are your pupils right now, right? That gives us very important signals that can show if a person is under stress or like what type of emotional response they're having to a specific experience. Head tracking is also an important modality of data that can be utilized with this type of VR headsets, right? On the flip side of it, I don't have it in the slide, like one thing we have to remember with using VR headsets is the accessibility issue, right? Because VR headsets are expensive, right? So it's hard to scale up. So a lot of our projects we develop actually for both VR and non-VR as well. But as I said, as VR headsets become cheaper and cheaper, it is the future, especially for for application scenarios like this, right? So what is the role of AI? Because it's in, like, as I said, my research sits in at the intersection of VR and AI, right? So how are we combining this, right? So the reason to utilize AI within our framework is that the therapy or the experience that we are providing needs to be both interactive and adaptable, right? If we just show a video and the video remains the same through all the sessions of a patient going through, say, like an exposure therapy, going back to the spider, if one little spider is crawling around in your room all the time, right? It's not going to be it's not going to help you deal with a real scenario where the spider is coming towards you, right? So like you not want to like increase the intensity of the experience or decrease the intensity of the experience based on your emotional response, right? So that's where the adaptability based on the assessed stress level comes in handy, right? So this is also in literature, it's also called biofeedback-based serious games, right? So serious games is the big research umbrella that is utilized in this case. Like we are gamifying some aspects of, say, like behavioral therapy, right? So as you can see, the overall framework looks like this, right? That if a user is wearing a headset, you can have a monitor right here, where there's a webcam attached, and the webcam can track the facial expression. Nowadays, headsets also have some facial expression trackers built into them, so maybe the monitor won't be necessary anymore. And the user is wearing a wristwatch, where like a wrist-based sensor, where we can get data like ECG, galvanic skin response, and temperature, right? So we can also get eye tracking, EEG interaction. We can get facial expression. You can also get speech data. So many modalities of data that can be utilized within our AI model, right? And the model's responsibility will be to assess the stress level of the participant, right? So the inference from the AI model will be the stress level of the participant. Once the inference comes into our adaptive game engine, what happens within the game engine is that based on that inference signal, we can up the intensity of the experience or down the intensity of the experience. That's where the biofeedback comes in so handy, right? So imagine that if you are doing like therapy sessions, like 10 therapy sessions. So again, like as you get adapted to the experience more, the experience adapts to you as well, right? So this goes both ways, right? You can increase the intensity, decrease the intensity, and there are many other variables that go in here. So the first thing I want to go in is the AI model, right? Then I will go back to like the VR experience itself, because as I said, like this talk covers two different things, and we're merging two things, right? For the AI model, the wearable technology plays a big role, right? Because we need actually physiological sensing data. So I usually talk about two types of data, physiological and behavioral, right? So physiological would be your ECG, your galvanic skin response, skin temperature. It could be EEG as well, depending on what type of data you have. So not all data can be available all the time, right? Depends on the application scenario, right? So, but the large amount of data from wearables, and from that, what we need is a stress or emotional response assessed from unstructured data, right? So we have a lot of data, we have a label, and we do an inference, right, to get the label. So that does sound like a dream AI problem, right? Like, oh, it's like such an easy AI problem. You have a bunch of data, you have labels, and you just do inference and assess stress level, right? But the problem is, where are we getting the data from, right? So in this area, you know how we have like data for image classification, like ImageNet. Everyone knows about ImageNet now if you are a comp sci student. So stress data is not as straightforward to collect, right? Because stress is very subjective in nature. It also, the baseline of stress also varies from person to person, right? So as you can see, this is the valence arousal model that is usually used to assess stress level, right? So usually what happens is when data set is created, for example, these two data sets we have here, WeSat and Amigos, these are popular public data sets, right? What they do is they show the user a video, and then they ask them to like click on one of these labels, right? So this is called the self-assessment mannequin scale, or SAM, right? And you click on the SAM rating, and the rating gives you your arousal or valence value, right? Based on that, you can calculate your stress level, right? So the problem with that is that usually these data sets, they ask the user to assign a label for an entire video, right? So we are not really getting the adaptable interactive experience that we crave for, right? Because if you see a 15-minute video and then say that, okay, I found this video scary, I was unhappy watching that video, that doesn't really give us a granular level of signal that we will require to create an adaptive interactive experience, going back to our framework that we have shown before, right? So the first research project that we embarked on, so that this whole project started back in like 2018, right? So that we wanted to create a new data set where we can do multi-level stress assessment. So this multi-level is important as well, because we can't just say that stressed versus not stressed, which is what most of these data sets do, right? So what we have to do is we have to have multiple levels of stress, because we want to use that signal to control our VR experience, right? So first of all, it has to be multi-level, and then it has to be an in situ stress assessment. By in situ, what I mean is that the experience is broken down into smaller pieces and stress levels are associated with it. So what we did here was that this is actually an interesting human-computer interaction problem. Like while you are watching a video, how do you label that what your stress level is? It's actually very difficult, right? Maybe you can have a joystick in your hand, but then again, you're focusing on clicking the joystick. That takes away from the experience itself. So we have not been able to solve that yet, right? So this is an interesting human-computer interaction problem that we will be focusing on in future. But right now, what we did was we just labeled the video externally by 3 raters, which is a controversial take. Like the paper, like when we published the paper, there was a lot of back and forth with the reviewers on that, right? Because again, stress is subjective, right? But if you look at the video, you'll know that the video we used is kind of a standardized video for stress, right? So I'll show it now. So this is the video. So this video does not have any sound in it because I want to explain why while the video is going on. So as you can see that the stress level was generally rated like this, right? Like low stress is just normal conditions, as you can see the label right at the bottom of the video. And medium would be like a moderate stress where a roller coaster is in some movement with none or few loops, right? And high stress would be that when the roller coaster undergoes multiple events of high activity. So this is a 6-minute video, so I'm gonna skip to some parts. For example, this is stress level 2 because you have gone up and like going slowly down, right? So again, some of you may disagree or like, are you kidding me? This is very stressful, right? So again, it depends on the rater, right? So we did find a good inter-rater agreement, right? So let's skip to some high stress situations. So this is where like it's very high stress. As you can see, a lot of things going on. The roller coaster is upside down. So when you did the data collection in the lab, right? Like some people actually at this point had to take their headsets off, right? They're like that, okay, this is getting too intense, right? Because it's in VR. So of course you're going underwater, coming over water. So, but as you can see that this is how we essentially broke the experience down into smaller segments with more granular level of data labeling, okay? So after labeling comes, so like, as I say, like the labeling and the dataset collection itself was a very involved process because of the uniqueness of our new dataset, right? So one important thing to mention here is that once you have that dataset, right, of course, then it becomes kind of like a so to speak, a traditional machine learning problem, right? So by traditional, I mean is that it's still there's a lot of innovation that you have to do on the machine learning side as well, because again, you are trying to assess stress from physiological signals and behavioral signals, not a lot of research in that area, right? It's not like, as I said, image classification or computer vision problems, which have like thousands of benchmark data sets, many models, right? So it's a slightly different problem, right? So what we did was, so this was our first the machine learning model that we proposed. We have many variations of it now, right? We have proposed some new ones as well. So as you can see, it's at this point, it's not really true multimodal. That's something that we are conducting currently. We're just using the ECG data and correlating that to stress, because we just using ECG data. There was a reason, because this was an industry funded project when we started, right? ECG is the easiest modality of data to collect because you just have to wear a wristwatch, right? That's it. So with the ECG, what we did was we still proposed a multimodal fusion model, right? Multimodal fusion is essentially if you have different modalities of data. In this case, our modality will be the raw ECG data and a spectrogram version of that data. You can also call it multi-view because it's not really true multimodal, right? But then what we do is the raw ECG is passed through the 1D CNN, right? And the spectrogram is passed through a ResNet, because ResNet is good at image data, right? So we're converting the ECG into image, and we're seeing that feeding both the image version of the data, which is spectrogram, and the raw ECG, like does that create a better machine learning model for assessment of stress from this type of data, right? So from the fully connected layer of 1D CNN and the pool 5 from ResNet, we take our feature vectors, and then we perform a weighted average fusion. This is our proposed model that gives us the classification. So the weighted average fusion, essentially what it does is, this is the weighted average fusion block, right? So from the 2 feature vectors that we have, we calculate the covariance matrices of the 2 feature vectors, right? And then we compute the eigenvectors and eigenvalues for both covariance matrices. And then we take the eigenvectors corresponding to the largest eigenvalues, and they are considered as the weight vectors of W1 and W2 weight the features respectively. So as you can see, if you have taken a machine learning course, this is akin to like kind of doing principal component analysis, right? So the idea is that the eigenvectors corresponding to the largest eigenvalue will give you a very discriminative representation of the data for the two feature vectors that combines the features in the most optimal way, right? So the reason of doing this fusion is that, of course, we could have just concatenated the features, but that makes it a very high dimensional problem. And we have also shown in other papers that concatenation actually, like the weighted feature fusion works better than concatenation, okay? And this type of fusion, the good thing is the feature dimensionality remains the same. So when we increase the number of modalities in future, that's what we are doing now, right? What will happen is that this weighted feature fusion, the feature vector dimension is going to remain the same, which is very attractive for multimodal problems, because as modalities increase, we want to keep the embedding space, like the dimension of the embedding space still reasonable. In this case, it's going to be the same always, okay? So some results from this model. So the first result here, what we're showing is that if we just use the 1D CNN, so the reason that I show the results for per subject is because, as you can see, like there is an important thing to remember here, that why stress analysis is such a difficult problem to handle. Like across subjects, the performance varies a lot. If you look at the first column, right, as you can see that, so this cross-validation is called leave one subject out cross-validation, right? So you'll see that a lot of data, a lot of papers in this stress analysis domain, they do like classic cross-validation, like say 90-10 split, right? And then average across. But that will, like if you do that on this data set, that's gonna probably give us like a 90% accuracy, right? But that means that you are looking at the test subject's data, which never happens in real life, right? So, but as soon as you do across subject cross-validation, right? So leaving one subject out, that's the testing subject, right? And then train on the other subjects and test on that subject. As you can see, the results drop a lot. And the important part is that the accuracy varies a lot across subjects, right? Like for example, for subject 11, we have 45.3, right? But for subject 13, we have 70.6 accuracy, right? So that's a huge gap, right? So we are averaging it. Average is still low, lots of work to do, right? But the important part is the standard deviation here, right? It's very high. So 1D CNN, then resonate with spectrograms gives us slightly better results. Of course, we have 2D data. Resonate is with the residual connections is a better model than the 1D CNN. It works better. But when you combine them, we're getting a decent enough boost, right? So if you look at it, 63.4 for spectrogram, and we're getting 66.6. That's a 3% accuracy boost, right? So like that's for our own data set, right? And our own data set has some limitations in terms of like the data set isn't that big. For each subject, we don't have that much data because of the limitation of how we collected the data with the granular experience, because for each subject took a long time to collect the data, right? But we also did comparative results on the popular WSAT dataset, and with WSAT, as you can see, that we get a pretty decent boost, right? 67.5. From there, we can go to 72.7, right? That's a 5% boost, right? Again, important to remember that we are sticking to leave one subject out cross-validation. If you look at WSAT results, like just go to Google Scholar, look at WSAT results, you'll see like there's 90% accuracy, 93% accuracy, but all of those papers are doing tenfold validation. And that, in my opinion, that does not make any sense for an application scenario like this, because you will never have labeled data for the test subject when you are actually deploying it in real life, right? So that's why it's very important to remember that for any type of medical experiments, that we should always do subject-independent studies, okay? So as you can see, the proposed fusion method gives us pretty decent results on data sets. Then what we have here is we proposed a new data set as well. This was published in IEEE Sensors Journal recently. And so again, okay, well, fine, we have done some good research on the AI side, right? But accuracy tables are good engineering. They're good to publish, of course, like as you know, academia is publish or perish, but we cannot lose sight of the goal of achieving real world impacts, right? Because that's the whole point, right? Like I talked about all this behavioral therapy, like therapy for kids, right? So where are those results, right? So what we have done is, after development of the proposed framework, we have applied that in different application areas where stress monitoring reduction combined with biofeedback VR experience can make a difference, right? So for the second half of my presentation, what I'll be doing is I'll be showing 3 ongoing case studies on this framework, right? That this is the overarching umbrella of like these projects in my lab, right? But we have applied that into different areas. So first one is a case study of cognitive behavioral therapy platform for kids with ASD, right? So this project is with the private partners are Shaftesbury and Unlimited Incorporated. They are the VR game development companies. Shaftesbury is a media company, and then Holland Bloorview Kids Rehabilitation Hospital are the clinician partner in this project, and this project has received a healthy amount of funding from these funding agencies. So what is this case study? So CBT is one of the principal mediums of treatment for kids with autism, right? Again, huge demand, lack of resources. We don't have enough therapists to perform CBT for all the kids. And as you know, that autism is also on the rise, right, across the world. It's probably because of diagnosis, because diagnosis has become better, right? So a serious gamification of CBT can be beneficial, but one important thing to remember is that it always have to be clinician in the loop, right? We can't just let an AI and a VR game go haywire on kids on the spectrum, right? So it has to be that the clinician, while the experience is going on, the clinician is sitting in front of a dashboard and they are monitoring everything, right? Everything that's going on. And not only that, the clinician also has control over what type of stressors are being introduced to the kid, right? So remember that when I proposed the original platform, the idea is that the AI is going to control these stressors, right? So here we are taking a step back, that AI, of course, AI can control the stressors, but we are not there yet, right? That is the ultimate goal, but we have to go slowly, right? Especially when we are working with vulnerable populations and sensitive populations, right? So what we did here was that first of all, we are creating actually the game creation is almost done. The data collection will be this fall. We are creating a game named Subway Sensations, where participants go through the task of riding the TTC, right? So it's stressful for many kids on the spectrum. I mean, riding the TTC is stressful for everyone, right? But especially for kids, like there's a lot of noise. The train sometimes suddenly stops in the middle of the tunnel. There are many people speaking in many different languages. Some people are loud. There's a lot of crowds, a lot of stressors, right? So what we do is, in this game, different stressors are very gently introduced. So that is the part of exposure therapy, right? And we have the clinician-facing dashboard to review sessions, not only review, to monitor sessions as well, right? So as I said, this study, the data collection for this study is currently underway at Holland Bloorview Hospital, right? So these are some screenshots of the game, like again, still work in progress, right? So I know that if you are used to playing AAA games, they don't look that exciting, right? But the idea is, the idea is that you are loading it in a VR headset, right? So it has to be low res, number one. And number two is that the more important part is the clinician facing dashboard, right? So as you can see that, like the clinician sets up the experience here, right? So you have different stages, right? So for example, you have low, medium, and high stages, right? So as you can see, in the lowest stage, there will be 3 non-player characters. There's subway car noises, ambient conversation, people walking. And as you can see, as you go up the level of difficulty, right, the stressors increase. Remember, that's what I was talking about when I talked about like biofeedback-based interactive gaming, that it has to be customizable. Right now, the clinician is the customizer, but eventually it will be a clinician AI collaboration, okay? And as you can see, in the game, you can actually like individually change each aspect as well, like sound effects, how big should be the sound effects, because as I said, especially working with kids on the spectrum, some kids are extremely sensitive to sound, so you would want to lower the volume, or if you want to expose them to loud noises, you increase it. So this is all decided by the clinician, because as engineers, we don't have the capacity or the knowledge to decide these things, right? So the clinician is going to decide all of these things, right? And then as you can see that while the child is going through the experience, they also have a real-time view of what they're looking at, right? And how long is left. So it's like a real-time streaming platform, right? So it's an online platform where the clinician can sit and watch the experience, right? And at the end of the experience, right, at any time they can log back onto the platform and look at review the sessions, right? For example, here, as you can see, they can review the ECG data, and parts that are labeled by high stress, like parts that have high stress will be labeled, and they can actually click on this in dots and see that what really stressed the kid out, right? Because that's the whole point of exposure therapy, right? So this project, as I said, the data collection is currently underway. Like this type of clinical project, as you know, it takes years for us to publish results, right? So, but I wanted to show that how we are trying to achieve real world impact with the algorithm that we have been developing, right? So this is where the algorithm comes in handy, because we can get the stress levels from the algorithm that we have developed, okay? The second project I wanted to show, the second case study I wanted to show was a refugee mental health literacy project that I have been doing with U of T and the Young African Refugees for Integral Development, YARID, right? And this was funded by Grand Challenges Canada and also Shark. We recently got a Shark funding for this as well. So this project, the context of this project is, again, as I said, the overarching theme is that how can VR improve lives by reducing stress, right? So for this project, we did this project, as I said, this is an international project. We did this in Uganda, right? So Uganda is the largest refugee hosting nation in Africa, right? And mental health stigma is a big problem, right? So before you can even go to mental health therapy, first you have to reduce the mental health stigma that people have, right? Because as you know, like in the global south, a big problem is that like mental health issues are very stigmatized, that okay, like that's not really a real problem, right? So this project was that how do we teach them like better about mental health, right? So we did a VR intervention, same way as the other project as well, right? So that was conducted in 2022. Currently we have published one paper on it about the protocol. Like the results paper are currently underway, okay? So I'll show a demo of the video of the experience, right? So as you can see, this is a real photo from Kampala, right? So we did the recreation, but this VR was actually created in my lab as well. Like we didn't have a private partner for the VR creation. And then the intervention was done through our algorithms that we have developed. So I'll play the video. So the next part of the video shows
Hello,
the
my
actual
name is-
experience where essentially there was a conversation with so the idea is that you put on your VR headset, you walk through the recreation of Kampala, right? Then there are NPCs in there where you can have a conversation. So these conversations were designed, as I said, in partnership with U of T, where we're working with the Faculty of Social Work, Dr. Carmen Logi from there, right? So their team developed this conversation. So these conversations were taken from a non-VR study that they have done, right? Where the conversations were evidence-backed, of course, right? This conversation was like this project was extremely difficult to implement in the sense that it's a very low resource environment, and there are we had to translate this to 5 languages, right? So of course I put the English one here, right? So but the people speak Swahili, people speak French, and I forgot the other 2 languages, right? So like that was the part, like that creation. So sometimes this type of groundwork is not really rewarded in like computer science or engineering, right? Because that, okay, oh, you did all this, but that's pretty obvious. Where's the research, right? But as you can see that impact, I think sometimes like impact is what will create groundbreaking research, right? So the groundwork that we put in has actually affected in a lot of positive aspects in mental health literacy, right? So I'll play the rest of the video. The conversation is a little hard to hear because it was again recorded in precarious conditions as well, because we had to use volunteers and people we recruited from Kampala, right?
Is Daniel and I'm a healthcare worker. How are you doing today?
I'm feeling really frustrated today because I cannot stop thinking about all the things I don't like about myself, and I don't know what to do.
It's really important to try to be kind to yourself. You can try to focus on being patient with yourself, even when you do things wrong.
I get it, but sometimes when I feel upset with myself, I can't stop thinking about it. Like sometimes I blame myself for everything, I blame others. I blame other people for all my problems.
So this is a small segment. This was a very long experience, 15 to 20 minutes, right? They go through 3 or 4 different conversations like this, right? And then after that, we did a post experience session that to see that if their mental health literacy has increased, right? So the idea here is that the person they're talking to, that's who they aspire to be, right? Like that, so that you can have better conversations regarding your mental health issues instead of completely discarding it, right? So within that, as you can see in this project, the AI aspect of interactivity, again, we are going to be slowly introducing it. It's a work in progress, okay? And the last case study I wanted to present here is de-escalation training for first responders in mental health crisis response. So, you know, the previous project was about stigma, and this is about like when first responders go to respond to mental health crisis, how do they de-escalate the situation instead of escalating it, right? So this was in partnership with Dark Slope, a private VR company in Toronto, and it's been funded by NSERC, and we also recently got a New Frontiers Exploration grant for this project. So the background of this project is that unfortunately, like whether we like it or not, first responders have become the de facto mental health workers when a person is going through a severe mental health breakdown, right? So de-escalation training is an extremely important aspect, right? Because many cases end up in violence, injury, or death. Because first responders are not mental health workers. They're not supposed to be, but unfortunately they are, right? So that's why they go through extensive de-escalation training, right? So currently the de-escalation training is conducted in person, which requires actors that are acting out to show like a mental health breakdown, dedicated space, and it's very hard to scale up, right? So a lot of first responders do not really get de-escalation training, and that results in this type of violence and injury, right? So virtual reality-based de-escalation training can be a very interactive experience, right? And performance evaluation, this is where our AI comes in, right? Instead of like, it's not only about the interactivity of the experience, right? We can also evaluate that the person who's performing the de-escalation, are they calm enough to actually do de-escalation? Because if they get agitated, they're not going to be able to, it's going to come out, right? So here we are using a body head tracking, physiological sensing. We also recently started working on voice data as well, okay? This case study is currently being done with the Ontario, like the Toronto Police Service, right? Again, we have done a lot of data collection for this. The data analysis is currently ongoing, okay? So I'll show you a small video of the VR experience, right? So I just have to warn you, like this can be a little distressing, right? But I have cut it down to like make it very short, okay?
Hi, Evelyn. Thank you for letting me come in and check on you. My name's Paul. I'm with the police. The reason I'm here, Evelyn, is your mom, Geraldine, called
So I just want
and
to
told
say
us that she was worried
cop
about...
here, like the cop is actually someone wearing a VR headset, and it's their embodiment, right? And the non-playing character is the person going through the mental health crisis. Because what we are trying to evaluate here is if the police, if the cop is doing the de-escalation the right way, okay?
About your safety and well-being right now. So So you look really upset to me. It's very obvious, and I'm just trying to figure out how I can help you. Can you let me know what's going on right now?
I'm not gonna get my kids back.
Okay, Evelyn, I was reading something on the way over here that said CAS was here. So were they here to apprehend your children? Okay, well, I'm sorry to hear that. It sounds like that's very upsetting, and I know it would be to me. I'm a father as well, so I know what it's like having my children around me. They're a great support in my life. And it seems like that's upsetting you that you don't have your kids. Is that right? Okay.
Yeah.
Okay, Evelyn. Well, thank you for telling me, okay? Thank you for being honest with me.
As I said, like this.
Hi, Evelyn. Thank you for
distressing, so I cut it down to make it very short. Again, this goes on for like 5 to 20 minutes each experience, right? And they go through a de-escalation training, that whether they are being able to respond to the NPC's simulated mental breakdown, right? So as you can see, there are a lot of potential of interactivity here. We are slowly incorporating that based on how the de-escalation is going. If you do like say speech to text, and then see that what type of words they're using, based on that, if the NPC's behavioral changes, you can make it a lot more interactive, right? And we are also trying to incorporate some generative AI technology for this project as well, because that will be useful for a dynamic non-playing character creation, which is very important, particularly for this project. Okay. So these are the 3 case studies I wanted to present, right? To summarize my entire talk, right? As I said, I went through the importance of VR therapy, right? For mental health intervention and other kinds of intervention, in general, digital therapy, and how multimodal stress recognition can be used as a control signal here to create biofeedback-based games, right? And I showed 3 case studies. So the current work that we are doing is true multimodal evaluation, because I have been using the word multimodal, but it's not really multimodal at this point. We have only worked with ECG, right? So currently incorporating eye tracking from virtual reality headsets, right? And we are also looking at the modular design of the clinician or facilitator facing dashboard, so that we can utilize that type of dashboard in the other projects as well, because we have only the dashboard for the first project, but the other 2 we don't have a true dashboard yet. And incorporating more human-computer interaction aspects. So if we have any, like, we're looking for HCI experts. So if you are one, please contact me. So design choices, labeling the data, how to do longitudinal studies for this type of projects, right? So these are very important aspects. And we're also looking at more application areas in workplace or workplace health and safety, or in healthcare, some other domains as well. Okay. So these are the major publications for the project. So like we have been getting pretty good reviews from the reviewers as well. It's again, like, because of the interdisciplinary nature of the project, right? Sometimes things get controversial. For example, the first paper that's in press, that's actually our first paper. We published the others, but that paper went through so many rounds of reviews, right? In like different journals. Finally, like published it at the IEEE Sensors Journal recently. Okay. And that's my talk. I must acknowledge all the hardworking PhD students, postdocs, and master's students I have in my lab. So this is a lunch that we did. I think this was right after COVID or pre-COVID, I forgot. It looks like pre-COVID because people are happy, right? Just kidding. So I do have open positions for, I'm looking for always for great master's, PhD, and research assistants, although I'm in engineering, but as you can see, my research mainly is in comp sci. So if you're interested, feel free to contact me, okay? All right, thank you, everyone.